Hello, everybody. I'm Josep. I'm a PhD student studying physics with an emphasis on nanosatellite optical instruments. And I'm here with Hendrik, who is...
I can do an intro. So I'm also a PhD student, but mostly working every day on robotics and autonomous robotics, basically.
And so this is our third episode of Thingy. I think we're calling it Thingy now. That's better. So basically the idea is to go through papers, interesting, at least for now, interesting machine learning papers, and see what we think about it. Our opinions are mostly wrong, and and so on. But yeah, so the idea is to learn, and one way to learn is to have a podcast about it, definitely. So the last two episodes we've been looking at neural Turing machines and differentiable neural computers. So which are basically neural networks where you just add the memory to it and see what interesting things you get out of it. The main thing you seem to get out of it is a bit better generalization than other best-in-class networks, which was long short-term memory. And one of the main way that they were teaching their neural networks was via curriculum learning. And although I think the name itself already says basically everything about it, then we still wanted to look into it, what it means more exactly, and what is the like state of the art in it currently. So for that, we chose the seminal paper, or the main paper that brought curriculum learning to neural networks, or perceptrons, because it's not the newest paper. Yes, so yeah, basically. So how we're going to do it is basically we have snipped out, so of course go read the papers, they're interesting papers, but we've snipped out the most interesting parts that we found in the paper. So we are either quoting them or we snipped out these images, so we thought that we should talk about. But otherwise, yeah. Maybe Henrik, you want to say something?
Maybe we can get right into it.
Okay.
Like what the main premise is, and then we can add as quite quickly, most likely to do a bit more general context about what it is and what it does and why it should work, etc.
So the main idea behind it was actually very well stated in the second paper. So we're going to scroll around here a bit. So there we also looked at the survey paper, which basically talks about the state of the art. And I quoted it here. Actually, I have. So basically, since neural network architectures are inspired by the human brain, it seems reasonable to consider that the learning process should also be inspired by how humans learn. So the basic idea was to recreate how humans learn, that as children in kindergarten, in middle school and primary school, we learn from relatively easy things, and as the years go on, we grow and we get introduced to much more complex problems, and so we learn iteratively, bit by bit. And so these people wanted to find out if this is actually useful also for machine learning. And so basically what they found out, this has a big impact, and we will get that to that. We'll get to that and their claims later.
I'll contend the claim big impact right away. So about how large the impact is in their, at least in the original paper discussions and training results.
I mean, I guess the impact was definitely big because it created the whole new.
Well, the impact of the paper is big and the concept is big, but was the impact that they got in their results big? I would claim no.
Mm. So
and also I would like to also add that this seems like a very intuitively obvious thing So the main concept, basic idea of curriculum learning is that we introduce a more complex problem over time. So the second paper generalized. Initially, it was only mostly described increasing the complexity of the data given to the neural network, but the other paper also extended it to basically being a more complex problem. And so you give it iteratively more complex problem, and the kind of basic assumption is connected to how humans learn, that therefore the neural network should also learn better. So I would say it's like sounds very intuitive. So I would say that everyone has a very large bias initially to say this thing works.
And there are also, like, besides, like, think about it, there are also, like, better reasons why it works, besides that it seems intuitive and reasonable.
Yes, but I would say that before we even start, I would say I definitely had a bias. Initial half an hour was very optimistic.
And then, but Henrik is a cynic, so.
Yeah. Yes, I have some problems with the claims of how far this goes. And actually, I think I would have more. I have a problem maybe with their approach, but we'll maybe get to that later after we explore this thing overall a bit.
So of course, when we're talking about basically giving a training network more difficult examples, the main questions are how do you I guess judge the difficulty, and how do you know when you go to more difficult examples? And this wasn't really talked about in this specific the first paper. So this has been more researched in the coming papers after that. So basically, yeah, I think this for all of these quotes are giving you the intuition why this should work. Is there anything specific we should talk about here?
Yes, some interesting claims. First, humans need about 2 decades to be trained as fully functional adults. That's an interesting one, because I think there is an interesting parallel to some animals and how they operate and learn. So and or not learn in that case, if it's presented like that. A good example is some kind of an antelope or whatever different similar animals where there is a lot of predators, where they basically the moment they are born basically have to start evading predators.
Yeah. So basically they come out fully functioning, but the humans basically we can't. If we would spend that much time relatively in the womb, then the issue is that we would all be killing our mothers, which is not nice, I think.
Yeah. I think it is very importantly that this is trying to match human learning, not animal learning, basically. So it's not just matching any biological process that has, like, it doesn't relate much to, like, say, non-human learning. It tries to match human learning very specifically. What was the interesting point here? I have more to say on that note, but I think the quotes in the second paper are more relevant to that, so we'll keep it to that.
Okay.
More important stuff is that the main positive effect is on the test set, which, well, that's the only thing that matters, so that's good.
No, it's not the only thing that matters.
Well,
real world effects matter.
Oh yeah, but
this can still be skewed, biased.
Fair, but it's better than the other sets.
Yeah, actually, I'm actually currently taking a course called special course in machine learning, and the whole idea there is the uncertainty and calibrating your neural networks. So talking about test sets and what actually happens in real life.
Interesting. Yeah, there is quite a few, let's say, introductory quotes that explain what it does, as we mentioned before.
So,
but one interesting part about this code that you had in front of it is that they basically move from this easy set of examples, so sampling from a set of only easy examples to sampling from a set of easy or like easy and hard examples, and they're progressively doing like increasing some kind of a weight, and then but still sampling from both sets. Basically.
It's also interesting here that actually, if we look into the survey paper later, we most likely won't talk about this specifically, but there are some people who approached it exactly the opposite way. So they started with hard examples, and that also worked. So I guess
that's kind of where the original problem comes out. If you have a completely opposite idea and that also works, then maybe something else is also going on.
Yes.
And I would say one very important thing here is some selection bias. One really triggering part about this paper is like at the end of most chapters they had the magical sentence that these results are statistically significant. But that doesn't mean that they are true. Good luck. You chose like sample sizes that are big enough. Congratulations. But realistically, like if your test setup is bad, it's still that doesn't mean anything. So that was something that was a bit weird about the paper, definitely.
Okay, then we get to their like, let's say, official definition of what is curriculum learning. So I'm just gonna read it out once. We call the corresponding sequence of distributions Q defined by lambda, i.e. curriculum if the entropy of this distribution increases. So the entropy of Q is smaller than the entropy of the next distribution, the entropy of the next Q basically. And the weights are monotonically increasing for all the next time steps. If that's, I guess that's a bad way of saying it. But the idea, I guess about it, how I think about it, and if it's wrong, is that you basically you have your whatever training data, and ideally, in the end, you want to use all of the training data. So this is you uniformly take samples out of the training data, let's say, and this is when your entropy is maxed, because entropy statistically basically says that the more likely or the more uniform distribution, the larger the entropy. So if everything is the same everywhere, then the entropy is maxed. But if everything is at one point, then the entropy is minimal. So a very unlikely situation. So basically, if we start take the sample, let's say in the first epoch or first go around, we only sample from a very distinct region from the training data, then we have a very low entropy. And then if in the next let's say exercise, we sample from a broader range, wide, let's say the Gaussian variance gets larger or whatever, then the entropy increases until we get into a uniform distribution where we sample the whole training set without any, I guess, bias. Is that a good explanation?
Yes, good enough.
Good enough. So basically, I want to find the most optimal way how to incorporate the whole training set. And their idea is that you don't want to take the whole training set originally, because you can have some, let's say, very noisy training data that might bias or let's say push the optimizer in the wrong direction and might end up in a bad local minimum, which can still happen the other way around, actually. But you want to have it like start getting in the right direction before you start adding the more, let's say, edge cases from the training set. And then there is the question, it's easy to theoretically create these data sets where you have, let's say, very noisy inputs because you can do some very simple things. But in real world data, how do you classify which are more difficult and more noisy problems? And then people have looked into that a lot. Anything to add?
It had one quote about the same thing, that if you try to learn multiple levels of abstraction at the same time, you might overfit. So if you try to learn, let's say you introduce one context at a time and have it learn that, and then another one, then the hope would be that you have to know context A, and then if you now introduce context B, you still know that those two things are separate, not that you need to overfit to just basically learn all concepts at the same time, or let's say fitting it in a way that you don't actually learn the underlying concepts, but you have mapped basically some very specific classification that separates those two contexts.
There's also one thing to add here about it and touch upon why the weights are monotonically increasing. It's basically that you want to put more emphasis on the later curriculum than on the beginning curriculum. In the end, that would be, I guess, more important than the beginning. Okay, so what quotes have you brought out and why, Hendrik?
So 4.1 was a setup where they basically had two different. So it's like the trying to ideally kind of show that the idea is good. So pretty much the way what I gathered from it is that they introduced. So first, this one is not done on a neural network. It's done on SVM. So it is still trained, but it is not trained or it is not necessarily applicable to a neural network. But basically, they create a classifier, and in one example they train the classifier using noisy data, and in the other one they train the classifier without noisy data, and show that the classifier with noisy data performs worse, which is in A, I would say, a very obvious result, and B, the error rate was 16.3% versus 17.1%. I wish I had quoted that here. Also,
I think this is the same one, right? No, this is
that's 4.2.
Yeah.
4.1 is very weird in any way, in every case. So basically, they show that they in one example they introduce noise, and in another one they don't, which obviously should make the result worse, but I would say the example here, or the result here, is it made it worse less than expected.
I know, but I mean, just one thing, just in case SVM is a support vector machine, basically, if you don't do any tricks, it's if your data is linear is separable. But you can do tricks that so if you change your basis basically, or you change your coordinate system, then you can also have non-linearly separable problem solved. But I think they used the noisy data in both of them, didn't they? Just the point is, when is the noisy data introduced?
Yes, but still, it's like it still uses the same amount of training examples. So let's say you still have more training examples with noisy data in one case, and less. Like, the problem is so weirdly set up that first, when I walked through it, I was like, wait, what the heck is this paper doing?
But I mean,
it has 50 training examples, which is not very many. So it probably doesn't overfit anywhere because it's so few training examples. And then in one case you have it includes a set of noisy examples, and in another case it doesn't.
I saw 2 points on this. One is like pro and one is against you. So I think that that's what they're trying to show you, is that you have this noisy data and it makes sense if you can't remove it in the beginning. The other problem is if you only have 50 training examples, maybe you're encountering noisy data more than you would statistically otherwise, maybe. So one is pro, one is against.
I mean, I see your point, but the problem setup is also very trivial. It is not a very complex learning problem.
I mean, that is the point. This is just like a toy example, a toy experiment. They're literally calling it toy experiments. Sorry.
But I mean, okay. Let's say it's not even an SVM. Let's say it's just a fitting of a polynomial on a data. If you give noisy measurements, your fit is better, or your fit is worse than with noisy data. That's basically what this is.
Yeah, but they're still giving it noisy data in them.
But less amount of total noisy data.
So that was my. So I mean, I guess I don't agree with you, but it depends on how much is their noisy data compared to all the training examples they have, and does that correspond to actual real world, I guess, amount of noisy data? Because otherwise, I mean, you always have the situation where noisy data, and if you can somehow remove it and then train it and then add it afterwards and get a better effect, then isn't that something you want to do?
No, because if you have Gaussian noise around the mean and you have a fit, then you still want, so when you add noise, all that happens with your, let's say, the line that you fit through the noisy data is, if you add noise, it might go off a bit because you have too few samples. Basically, you can't capture the whole like the noise accurately, but it's just noise. It won't classify better the final test set if it has seen noise before, because the noise
Wait, actually, no, they don't. Only with the examples.
Trying to read if it may like.
Actually, sorry, I was actually totally misconstruing what they did. Yeah, what they did here is just these examples. So I was arguing the wrong thing.
I mean, the things in the bottom make much more sense. I just have a problem with the first one.
I agree with that. I just misremembered, because I thought they also introduced noise examples in the end, but this is just easy examples, and then yes, of course, this is like a dumb example, because they say here the difficult examples are probably not useful because they confuse the learner rather than help it establish the right location of the decision surface. Okay, this experiment does not involve a curriculum strategy yet.
That also. I missed that part. That's even says less. Okay.
Yes.
Anyways, let's move on. Because I don't think I will be convinced this makes any sense in the context.
I agree. I just misremembered. That was my fault. Yeah, this seems totally useless.
Yeah. Then we get to basically perceptrons, which is basically proto-neural network training.
Can you in a few words say what a perceptron is?
Was it only one unit of a neural network, right?
I think it's still basically still you're trying to fit linearly separable problems, unless you do a basis change or a kernel trick, whatever it's called.
Yeah, but basically a perceptron, well, history of neural nets. First they invented perceptrons, then they added many together and you get a neural network. Basically. yeah. So perceptron is basically one neural net unit. You can kind of think of it like that. One unit in the layer of one neural network. And if you put many in a layer, you get one layer of a neural network. If you add many layers together, you get basically what is commonly known as a neural network today, because the one layer ones are usually not used at all. And then if you add many more layers, then you just, from some abstract number, you start calling it a deep neural network.
Yes. If you have more than, if you have hidden layers.
Yeah, if you have, I think, roughly more than 15, 20 layers, or even 10, more than 10 maybe, then I would already consider it deep. Anyways, small tangent done. Second example is also a bit weird, but less weird. So here I copied the statistically significant part because once again it was funny to me that this one is always brought out. I could have put it everywhere. But basically here is well, they mentioned the name of the thing is introducing gradually more difficult examples speeds up online training. But I did not understand how it speeds it up from the stuff that they wrote in the paper.
Well, if you look at the graph, then it's better always. So I guess it's speed it up. I mean, how do you define speed up? I guess is the question. So if we look at
total training time to reach global minimum.
You don't know when you reach a global minimum.
Yeah, but until it stops improving and you do easy because I think in the bottom stuff they also use this early stopping mechanism basically where
divergence in the test set.
Yeah, when you see that your model starts overfitting, you early stop. So the time it takes to reach early stop is what I would call pay, and relation of that to the size of the training set is what I would say how fast the neural network is. Anything else doesn't make any sense.
Yeah, they don't really clarify that part.
Yeah,
because even
the same goes when basically they mentioned, and this is basically probably related to the claims of faster convergence, where basically they claim that the using curriculum learning they reach faster convergence, but my point is that I don't see any supporting data under this paragraph nor in this image to support that.
Yeah, at least the statement is also they state the same thing in the other survey paper that this usually happens. So I guess we can take it, but yeah, they don't really show what they mean.
But the survey paper many times reference this paper when these claims are made. So so I will remain skeptical. Okay, having said that, the weirdest part about these graphs is anti-curriculum. So basically, they didn't explain how they set up the problem too much here. But if the no curriculum and anti-curriculum are very similar. No, they're not. Never mind. I got confused. No curriculum and anti-curriculum are similar, but in the above example, it is not.
So easiness based. I don't actually understand this very well. Average error rate of perceptron.
So the easiness is how they chose what how they plan their curriculum basically, and so they present two different strategies.
Yeah. But yeah, they don't talk about anti-curriculum at all, but I guess we can presume that it just takes the other way around. Exactly.
Yeah. So
And
basically, you want to show that curriculum is better than anti-curriculum.
And so the input dimension is basically
how many inputs the perceptron takes, and then they have different tests, 4 different basically trainings and 4 results for both. Well, I say 4, but 4 input dimensions, and then they do it with all of them. And basically, I would say this is one example where, as far as I could tell, it showed like a pretty good result for, like a positive result for curriculum learning.
Wait, so the average test error is larger?
Yes, if there is no curriculum or anti-curriculum. So.
Oh yeah, sorry, the curriculum is the bottom one. Yeah.
Yes. So the blue one is great.
Yes.
It's basically almost 2 times less error, and the error grows if you have larger input dimension. My main problem with these results is mostly that the errors are quite large, and I would imagine many different training tricks and tips and whatever would hopefully reduce the error a lot, basically.
But there's also the question that this is quite an old paper. So this is the paper is from 2009. So that's basically in the Stone Age.
Yes, but still the toy problems are so simple, you would expect much better results. So here the problem of it would be very good to see with all of these different curriculum levels how the error rate decreased over time. And why I say that is because of if we go a bit go to the last figure of the thing, which is this one.
Yeah.
So
I also had an issue with this figure.
Yeah. So basically, I would say this is like an anti-example of what they're trying to show.
I mean,
because it does not converge faster.
I mean, it does. In the end, it depends on how you define converge. If you define it by, I mean, I don't know.
Well, fair, but okay. I mean, yes, the rate is bigger, but only because the initials.
Well, maybe we're just very, what's the word? Ignorant, and we don't know the official definition of convergence.
Oh yeah, I mean, if you say that the derivative of this plot is larger with curriculum learning, yes, but that's only because like. I agree with my ignorance in convergence in neural networks.
So
let's go.
Let's see. We're looking at AI.stack exchange. What is convergence in machine learning? So an answer by Ashenoy, which has 5 upvotes, says that a model is said to converge when the loss is a converging series.
Yeah, but
faster.
Yes, but in that plot, there is no convergence set, so it doesn't reach the local minima in either case. So that's so the first point where it reaches a better result than the no curriculum to say, okay, done, guys, we finished this example. Sorry, don't have no more training resources. Don't know if it actually in the end, if you let it run further, maybe no curriculum outperforms it. Don't know because they forgot to add it to the plot, and they have claimed that convergence has been achieved, but no.
Yeah, I guess you just have to take the word about it that it in the end converge. Yeah, but yeah, I guess I mean, we already get the idea about what convergence is, that you just basically get closer to the loss in general terms each time step. But
Yes.
question is, when do you define that it is converged?
Yeah, but because
stopping.
There isn't one plot that shows that this convergence has been achieved faster with curriculum learning than with no curriculum learning, 0.
I think the idea here is that they show that, okay, you see, if we wait long enough, curriculum does it better, and trust us, it also converges faster.
Well, I know, but this plot doesn't show it converges at all.
I know. I'm saying that. Trust us, bruh.
I mean, I agree, but that's my point. This basically paper says trust us. It's in abstract. But there are no supporting plots. And then we have this other paper that also says, and it is very cool that it converges faster. Why? Because of this paper. But this paper
are there only references in this paper about that?
Yeah, fair. No, but well, I think the main part when they talk about conversions, that's a reference to it.
So you can. I will Google it, try searching for it a bit. You can continue talking.
You can see the multi-domain, like page 5 of the paper.
When we use only easy samples at the beginning of the training process, we naturally expect that the model M can reach higher performance levels faster. Yes, okay. This is because the objective function is smoother, as noted by Benjo. Okay.
Yes. Yes. And then in the next one, they also do the same thing. Like, once again, the next convergence thing that they talk about also talks about Benjo.
Okay. So in multi-domain approaches, Benjo introduced a set of easy and hard learning strategies, blah, 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 to show that the automatic models benefit from such a training, achieving faster convergence, while finding better local minimum offers conduct multiple experiments. Okay, the only reference. Okay, so I'm looking.
Having said this, this paper itself references another paper that has already looked at convergence in, which they don't call curriculum learning, but they basically the same idea. Mm-hmm. So somebody has already done some kind of it converges faster, and it seems like they trusted that and just said, we also show that. Don't mind us that we don't actually show it.
I guess we could just take it on good faith currently that it actually does converge faster, but maybe it's just a trivial thing that they're not bothered in showing it.
But that would have been very interesting to see how they, because that was one of my why I tangented here. This average error of perceptron, I would have wanted to see the graphs of how it converges, because that
and where they stopped as well.
Yeah, because right now it's really hard to say if they did like proper due diligence with that test, because
basically we can look at the same curriculum learning. So what they did with the language model, and we can presume that maybe if you have 500 million updates more, maybe the no curriculum one still goes past, right? Though it the progress isn't that fast anymore. Basically.
Yeah, I mean fair, but
that
would be that would be the exact thing you would want to see, though. Yeah. That's the most interesting result, in my opinion. But whatever, it's fine.
We'll take it on good faith currently that someone else checked them and it does converge nicely.
Exactly. Otherwise, it would be like, what the heck? How is this possible?
Imagine you're like, oh, okay, I'm going to test this stuff 13 years later. And you're like, oh, no, it doesn't.
Yeah. Anyways, convinced only because there's like a literature survey of 200 papers that uses this thing. But if I was the first one having to use that, probably no.
Yeah. So currently, this is a logical fallacy. We're trusting authority.
Yes, I say that I'm trusting them, but I also have very high skepticism at the moment because of things like this. Having read through this paper, so coming up something more realistic. You can show the image right away. I think that's a better part. So they did a state recognition test, and they separated it into easier examples and harder examples. Easier on the top and harder on the bottom. So basically triangles, circles, and squares on the top one, and ellipses. Not how is it called? How are these triangles called? Well, not triangles with the same angles in the
A regular triangle.
yeah, and well, rectangles instead of squares also. So basically, easy to see that there are easier examples and more difficult examples.
The one question I had, maybe they touched upon this, but a triangle with different angles is still a triangle, but a circle is not a circle anymore if you go to an ellipse. Same with the square and the rectangle.
Well, you could say that.
But yeah, round object for
a circle is an ellipse, but an ellipse is not a circle.
And an ellipse can be a circle. I know. Well, yeah, no,
well,
no.
Yeah. So my point is, yes. So, but I benefit of the doubt. Basically, in our logic, yes, those are, let's say, a bit different. But I could understand how they present those as learning a concept and then extending that concept.
Yeah, and also the other thing that they were varying with difficulty is, so basically, for those not watching somehow, or listening, that so you have a geometrical object on a background, and then you can also determine the difficulty depending on the contrast. So if both the object itself and the background are very gray, then you have very small contrast, and it's more difficult. But for example, if the rectangle is black and the the background is white, then you have like maximum contrast, and that makes it easier.
It makes it easier, they claim.
Yes, at least for humans, it makes it easier. So this comes down to what is actually difficult for.
Yeah, to that I would be a bit skeptical if that part is actually more difficult, because. But anyways. Moving on, they basically here they have a bit different formulation of curriculum learning, if I understand correctly, because now they have like a switch epoch approach, which is like they have at some moment where they switch to basically including these geometric shapes into training set. Did I understand correctly?
Yeah. So the current two-step schedule: perform gradient descent and the basic shapes training set until switch epoch is reached. So the question is, what is switch epoch? Then perform gradient descent and geometric shapes training set. So basically. So the question is how many times they switch between the examples, or?
No, as I understand it, it's like baseline corresponds to training the network only on the geometric shapes training set. So the switch epoch is 0. So they do. So when they switch only to geometric shapes. Don't use basic at all. So it is. So they have two different basically training sets, basic shapes and geometric shapes. And now the switch epoch says at which epoch they switch from basic shapes to geometric shapes. And what the plot shows that the later they do this, the better the results are. Now, the first question you should have is, why didn't they do 256? And that's my first question, because they still went better.
Yes.
So the second question you should have is, well, obviously, if you switch at 0, then you have less training data and it performs worse. So obviously, this is worse. And this is confirmed by the quote that I also showed, which says that if you combine basic shapes and geometric shapes into, the first quote here. Basically, if you add both the basic shapes and the geometric shapes to the training set and to confuse the reader, We trained a no curriculum model with the union of the basic shapes and geometric shapes training sets. Don't try to use union, try to use as confusing statements as possible. So the reader might look past the fact that no fucking shit you're supposed to add the both of them together when making the baseline comparison. But they wanted to prove that their thing is really great, so they didn't want to put the actual baseline on this graph. Anyways, rant over. It still seems to perform better, this idea. So the basic idea is good, but the experiments are holy shit how bad.
So basically, if we look at, like, if to understand correctly, if you look at 0, then this is basically they did it 128 epochs, but they never switched. Or
no, they with 0 they switched right away.
Okay, so they only used geometric shapes.
Yes.
For 128 epochs.
No, they had more epochs. They have. What is the total epochs? 256.
56. Oh, okay. Yeah. So yeah.
Yeah. So halfway. So the last one is halfway. They switched.
And but did they do one with which they had both of them from the beginning to the end?
Yes, that's the. But they don't plot it. That's the one where they say
the baseline.
Final test error is equivalent to epoch switch epoch 16.
Oh, okay, yeah.
So the one in the middle, roughly. So, but still, let's say, and they also say that they verified that with training only basic shapes yielded poor results, but not sure how poor. But still, let's say the setup and all of these examples are all a bit fishy and all feel wrong.
So yeah,
once again, I think it shows that the basic premise is pretty good and it works, but because they're not fully getting the conclusions that they want, because once again the error rate difference is like 0.02 here, and it might fully be that this doesn't like these very small errors don't actually generalize as much as they would want us to believe.
It would be interesting to see when you get so I guess the loss stops converging, so you get well, yeah, basically what would be interesting to see what happens after 128 epochs and so on. To have a nice line would be a bit more useful.
Because once again, if they claim all the time that this helps faster convergence, maybe the other training hasn't converged.
Also, like, how many different people did they have doing the figures? Like, this figure is so different than this figure. Like, what the fuck?
This is octave plot, I think. Like, there's some default.
This is a box plot.
Yeah, but it's like a default plot setting in one.
R?
Wait, I would say quickly what it is.
But I know, but it's still interesting, the criteria. Like here you have a nicely formulated plot. You have a title, you have a y-axis, x-axis, and then here you just have an x-axis.
That plot
and completely different.
It is Octave's box plot with default values, basically.
Okay. Okay, this is besides the point. It's interesting that they don't have like. Because all the graphs are different. But yeah, that's besides the point.
The main reason it was like somebody just made a quick 5-minute plot and it looks exactly the same. So that's funny. No, actually, that one has more detail. Sorry, the one that was made in another context.
Mm. And so we move on to the last experiment they did. And I guess,
yeah.
So here they basically, yeah, okay. So they trained the language model where basically the model had to predict they had the sequence of 4 words, and they had to predict the 5th word basically. if I'm correct. And they based it and they trained it this on Wikipedia through Wikipedia. And in the beginning, they used only the training set was based only the 5,000 most frequent words, and then they went to 10,000 most frequent words, and then they went to 15,000, I think. And then the training set comparatively always grew bigger and bigger. So they had this basically 5 word sequences with only the most frequently used words, I think. Right?
Yeah.
And so here we had also this is what so when I was reading, this is the main graph I had an issue with, because I was like, but why did it? So I just want to see basically the graph being twice as long to see what actually happens after this. Besides, bro, trust me.
Yeah.
It converged.
And I would claim that this plot shows either that it has better, like faster convergence, or that it that it actually performs better on a test set. Definitely not both.
So is this only test data on test data set?
The final error, yes, I think is like. I would assume that it's still done on test set. It doesn't say necessarily, but
so yeah,
but I would not. So it's basically if you train it more.
Just I guess a note on what this graph also shows is that besides that is that on the y-axis basically you have how probable is the 5th word so here this time it actually used a neural network, a small one, but a neural network with a lookup table, which was anyway. So basically this one shows how probable is the word that the neural network actually chose for as the 5th word. Right.
Mm-hmm.
Basically.
Yeah.
But so the main takeaway, I guess, from this paper is in general it seems to work, but all the examples are a bit iffy in the sense that they would ideally show more data. So I guess they do early stopping, and I mean they say they do early stopping, I think, but they should show the data series longer to see what happens after it. Is this the actual correct spot to stop, and what happens to both of these lines after they stop? They could have I guess for example, this graph could be twice as long, and they say, okay, we stopped training here because here the test and training data started to converge. Because I also this is for example, why this is important is because we have this graph, right? And we don't know, did they stop training both of these networks at the same spot at 1,500 million updates, or did they actually stop maybe the no curriculum one at 1,000 because it already was diverging from the test set so heavily? But we just don't know that because they're not saying anything about it.
Well, I mean, it still is. It hasn't converged from the graph, I think.
I mean, you don't know because the training set can already be going down, right? I mean,
yeah, theoretically, yes. But I mean, then in that case, no curriculum would be converging faster, and they said it's converging slower. So I would say the other way. Maybe no curriculum performs better, but they don't show it because curriculum has converged and they stop training, or who knows what is going on? Because we don't know.
This leads to dumb speculation from dumb people like me.
I mean, we don't know because they also didn't say. I would say. So, but my conclusion based on reading all of this and even here reading how large the errors are, if you would read this paper and you were solving the real world problem, then I would say don't spend resources looking at this. Spend your resources A on increasing your data set, B manually filtering out bad training data, or basically do anything else that improves your performance more and faster than the things that they have done.
Yeah. Well, manually removing training data seems difficult. I mean, if you want to remove training data, then you already, I think, you have some kind of difficulty measure, depending on it. Then you can already kind of incorporate it into this.
Yeah, but what I mean is, let's say you have mislabeled data, incorrect labels, stuff like that happens always if you like with pruning your data. Just let's say you have X amount of hours to spend on improve, or let's use another measure of resource. Let's use money. Let's say you have X amount of money to spend to make your final neural network better. And if somebody came to me and said, based on this paper, let's use curriculum learning, then I would say, no, it is not efficient.
I guess I would kind of disagree because let's say you have a very large data set. If you want to start manually working on it, then that takes pruning, whatever. That takes a lot of money and a lot of time. So it might be more cost effective if you can automatize it with curriculum learning, with some kind of difficulty measure or student-teacher network or whatever.
Yeah, I don't have a problem with the basic concept, but if I had just read this paper and somebody says, let's implement this, I would say you still almost have to do the same work. You have to do the same amount of work than just like pruning, because you still need to manually figure out these basically difficulties for all of these.
But all of the data. But there are already, depending on what's your use case, because at least from the survey, there are already some kind of like general, for some kind of problems, there are like some good difficulty measures that you can just incorporate.
Yeah, I mean, once again, I think the basic premise is pretty good. I just don't like the paper.
But it was an important paper.
Yeah.
So this can show you that even if it's an important paper, it doesn't mean it's a good paper.
Yeah, I would say that basically. Having said that, now it's like a perfect tangent to the other paper, and the other paper. If I'm already on this topic, I had one extra quote here, which is this is basically reflected in all the curricula taught in schooling systems around the world, as humans learn much better when the examples are not randomly presented but are organized in a meaningful order. I agree, but I would not say that the optimal way to learn is only going from complexity from bottom up in trying to approach basically problems bottom up. I think that's a shitty way to learn, and it does not generalize.
I think I mean, so there. I think they touched upon the psychology that it usually it's better to go bottom up for humans. I think there was some psychology. Let's say psychology of 110. Let's see where they reference 110. Where did they use it? Okay, so incremental or continual learning refers to the task in which multiple subsequent training phases share only a partial set of target classes. I know. No, this is not the one I was thinking of. But this somewhere referenced, I think, actual learning data. But yeah, but I don't know.
I'm gonna go all like a crazy person and go like, based on my anecdotal data, I think this whole full load of bullshit, and this is why the school system sucks, and burn this thing to the ground type of thing.
I think, like, from what I've gathered, as context, with both of me and Henrik have given the same course, actually. So we both give the course Introduction to Space Technology. Henrik used to give it to me, actually gave it to me, and now I'm giving it to other people. And I'm actually taking also a course on teaching. From what I gather is that you want to have this preview review. So basically, how I would understand it is you want to give the big picture, the context. You want to give them the inkling of what is the actual difficult thing you want to solve in the end. and in the end it is not understandable and difficult and bad. And then you go back to the simple things and you deconstruct it. And then once you get back to the difficult thing, then it all makes sense.
Yes. But very importantly, I would say like this full bottom up where you just go from you build, and then you magically become able to generalize knowledge. I think that is like the most insane thing that let's say is expected that works, but it's like one of the like if I would be a high school teacher and somebody came in teach this curricula and those work like that, I would protest heavily.
but I guess I mean as a high school teacher, they already have a lot of this bottom-up stuff from earlier classes, right? It all depends on what you're teaching and where you're teaching. If you're teaching higher education, your secondary, primary, I think it all depends.
I agree, but I would say I'm very radical about this. It's like it's my place to say the school system sucks, and this is the reason why. Because people think this is so obvious and intuitive that yes, we should all do this.
I wonder if I Google this in front of everybody, bottom up versus what would it be versus teaching versus teaching. Most likely will give me some kind of breakdown. Okay, the difference between top-down teaching and bottom-up. I think most likely this is actually
this is pretty much
a debate on it. So there are okay, most likely we're not going to tangent onto this too much, but I would presume this is not like a done deal. That how to teach it. This is such an open question on how to actually teach people. I mean, even starting from should you do a lecture or whatever when you're teaching. So I think stating it this heavily that this is the best way to go about it, I guess this is the way we've been doing it for years because it makes sense because humans are not the smartest. Not all of us are the smartest when we are 3 years old. So you can't really start with, I guess. You can still like. I remember reading.
I disagree. If I had a kid, then when he gets 7 years old, he gets calculus. That's it.
Maybe geometry first.
I mean, but let's say in two ways, because I think like those things that have like from the difficulty, not in like say implementation or like with this bottom approach things, the things that are, let's say, maybe implementation wise more difficult, but conceptually easier because they kind of extend this like they meet these high end concepts from the other side basically.
Mm-hmm.
So this is how the surface of a sphere and let's say algebra actually connect through integration and stuff like that, so that you always, let's say, make these conceptual links, and that is important instead of building up from whatever bullshit to, and then here are edges and here is a line and this is, and then this is a picture of this rest of the fucking owl picture basically. That's like school education. This is like here you introduce this easy concept and easy concept, then you get the rest of the fucking owl. This is because the integration and generalization is hard usually, not the actual, let's say, small nitty-gritty details. It's just very hard to learn the details when you don't understand the big picture.
I think you should never underestimate the ability for children to understand.
Yeah.
I also remember I was reading some kind of book. I don't exactly remember the book, unfortunately, but they were also teaching that. I think some math teachers in America somewhere, they were like, "Yeah, we don't really underestimate our children, so we teach them university high-level maths in high school, and it works out."
Yeah.
and they get into grade school, so you know.
Yeah, because it's like
the biggest issue, I guess, with those is that it really comes down. It's a lot easier to teach bottom up than to top down, because if you want to go top down, you actually have to have skilled teaching, And unfortunately, since teachers are underpaid, most teachers actually, a lot of teachers from personal experience lack the skill to teach, even most prominently in higher education.
Yeah. Well, this is such a fucking, let's say, agitating topic that we can't, I think, extend it fully. But coming back to this curriculum learning, I would claim that this, let's say, the initial setup of basically this curriculum learning, it was that let's just go from easier to harder. And now we have this survey that basically the most funny examples of this is we tried the opposite strategy, which was hard example mining, which was basically similar to this, where there was also anti-curriculum learning examples, which performed better than curriculum learning and so forth. So I think the problem here is that the space of how we choose these things is not not thought through thoroughly, basically. So it's not just let's go from simpler to harder. That isn't like a magical bullet, because apparently sometimes harder to easier works. Maybe there is a combination. Maybe I should have to think about more. Maybe it doesn't generalize that easily.
Actually, the second thought there is, I think, fun. Like, since neural network architectures are inspired by the human brain, it seems reasonable to consider that the learning process should also be inspired by how humans learn. Which is funny. It seems like machine learning or AI enthusiasts have like a love-hate relationship with comparing neural networks to human brains. At one point, these are like perceptrons, and this is how they work. At the other point, no, this is completely different. Nothing the same.
Yeah, we just match we just match data to manifolds, and humans don't match data to manifolds. Maybe, I don't know. We don't understand.
Yeah, but yeah, I guess so. I don't, maybe just so we don't misconstrue their point is that they don't say that. So this is basic. So talking about curriculum learning now. So this is basically reflected in all curricula taught in schooling systems around the world. As humans learn much better when the examples are not randomly presented but are organized in a meaningful order. So here they stay away from saying that easier to more difficult, but you have a reason to how you're teaching. That you're not going to school as a first grader and then you have a random pick of today you do this exercise from general relativity. Good luck, have fun. Let's see if you work it out or not.
Yes.
Well, I don't know how to read.
But having said that, we'll get to that maybe setup of the thing that you're shown here. But before that, one quick, I would also want to point out that once again, since neural network architecture are inspired by the human brain, not animal brain, it seems reasonable to consider they should be inspired by how humans learn. Which are on that level, are human brains and animal brains different on the level that neural networks today are? I would say no. I would say human brain differences are very specific and don't apply to. Well, I don't know which neural do we have. I haven't read enough about it, but my intuition says that, let's say, the current neural networks we have aren't similar to a human brain, but they're similar to a brain.
Henrik, this reminded me a new good title for our podcast. I haven't read about it, but
fair. Because I mean, it is a new topic for us mostly, but still, like, some things are very, let's say, connect to other things, and this is once again like, what the fuck.
Yeah.
Anyways, let's move on with the quote, because I think this organized in meaningful order becomes very important when basically this paper generalizes the.
It doesn't get generalized, but the goal of it is to say that, hey guys, we should generalize.
Yeah, fair. But still, basically that.
So one of the, I guess, key points that I've also brought out, this talks about this, that so in the last paper we have this the training data, let's say, gets more difficult, but so that means the experience of the neural network gets more difficult. But the issue here is that then you have to think about how because if you have a really large training data, you're not going to go, even if you go manually through them, like how are you going to define what is actually difficult or what is not? And you have to somehow, you should at least somehow automatize this, because otherwise you're going to spend loads of time and money. So so you need some kind of external measure of difficulty, and this might not always be possible, or if it's possible, you might not figure out how it is actually possible. So therefore, we can actually go from, we don't have to make the experience more difficult, but there are three ways to go about it. I mean, two of them kind of go together. I think making the experience more difficult or making the tasks more difficult. And the second way is actually just starting with a simple model and then increasing the model complexity throughout the test time. And and then you don't need a difficulty measure. I guess you still need to know when to switch to the next model, but it makes it kind of easier in a sense.
Yeah, you can probably figure out some convergence parameters, and if you stop converging, and then you can switch.
Mm-hmm.
Yeah, but I would say the model thing is conceptually very different than the other ones.
Mm-hmm.
And based on analogy, where we are using the human analogy here a lot, that would basically the analogy would be we give the child general relativity and and basic circles at the same time, but we just wait until the child grows up. But you always give him the same crap. You just let the child grow up but you always get general relativity every day. And we just assume that as he grows up, he will learn more on the general relativity side just because he grows up.
Yeah. So actually, I think for me, as I understood the paper, one of the third take was also that there isn't enough emphasis actually put into this making the model more complex. But they at least think that this is something that research should be headed towards. And like one of the examples that they gave with making the model more complex, I think, was that they smoothed out the weights, if I understood correctly. Gaussian. Me talking out of my ass without actually remembering what I'm talking about. And you can talk while I control F.
Yeah, I would say that this model-based approach makes a lot of sense to me. But once again, I said some of the analogies that we used before break down, while the task-based one is basically what if we have the model first predict from an image where a face is, and after it has learned where the face is, we have it predict where the eyes are and the mouth is and the nose is, for example. And you do it in different steps and hope that this helps better to, in the end, figure out all of this, where the face, mouth, nose, etc. are, because you have first had it predict something more general, basically.
Okay, the quote that I was looking for, I'm going to read it. So, however, we should emphasize that other types of curriculum learning, namely those applied to the model or the performance measure, do not necessarily require an explicit formulation of a difficulty measure. So this is the same thing we were already talking about. So contrary to our expectation, there seems to be a shortage of such studies in literature. A promising and generic approach in this direction was recently proposed by Sinha and others. However, this approach, which performs curriculum by deep learning convolutional activation maps to increase the capacity of the model, studies mainstream vision tasks and models. In future work, curriculum by increasing the learning capacity of the model can be explored by investigating more efficient approaches and a wider range of tasks. So basically, they're saying that not enough research has been going into this, and the only example we can find is one images, basically.
There is an interesting point here, which is actually that's not a good one. It's more on the task-based learning side. So I would claim that a lot of these curriculum learning, which is called curriculum learning, is maybe used but with different names.
I mean, they had a lot of names here. Say.
Yeah, but even then, I would say, let's say some classical thing. Like, I wouldn't go classical. Let's say some YOLO methods and stuff like that, which are like classical in robotics. And so 4 years old, YOLO V3 and stuff like that. You can basically, what the heck was then? I always forget this. Where you add have a ready model, but then you are able to let's say
the last layers between the
yeah,
last
but you're able to train with your own data and add to this basically model. So you take a ready model and you add your own data and you make it better, basically specialized.
What they usually, I think, how I've seen it used is that you basically, at least with fast AI, for example, you can, for example, download ResNet, whatever 54, which is trained on, let's say, ImageNet, and then you have a very specific purpose for it. And then usually the first, let's say, whatever number of layers, let's say n layers, are very like these general layers that are just like trying to figure out basic geometrical shapes. So what you can do is you can freeze all the the first number of layers, and then only train the later layers on the new data. And this makes the neural network more specific. And then if this isn't enough, then you can try unfreezing the whole network and retrain that.
But I would claim that is almost curriculum learning, basically. And like that, I would claim that is the model-based curriculum learning almost. It's just like presented differently, or let's say shaped differently, but it is very similar.
Where I first encountered, let's say, also like curriculum, I guess that is curriculum learning, is what was called progressive with learning. So idea is that in super resolution that you first, let's say, train it to generate super resolution of, let's say, ×2, and then after that you train it to 4×4, and after that ×8 or whatever, how far you want to go.
Yeah. So I would say basically, I would say this literature study, what we read, mostly focused on everything that mentions the word curriculum learning, but that is not necessarily the whole scope of
I know not everything
people thinking about the problem like that.
I think that is a wrong statement, because it's not everything in name coverage, because they like very specifically they have things called like self-paced learning and whatever. They have like loads of different methods. I'm not saying that they covered all the different ways that curriculum learning can be like thought of, but they had a lot of specific curriculum, but they had other stuff.
Yeah, I agree, but to me they felt like an extension of this basic premise, while things that come from a different direction and implement the same basic ideas aren't like thought of as curriculum learning, which we quickly talked about right now, which I mean I would claim are very much like.
Because basically the thing you talked about, I think, is called transfer learning.
Yes.
And I think and they talked about it here as well, for example.
Okay, then that one I missed. This one was very hard to learn. This paper was very hard to read because.
To say, I guess, to the two people watching, we neither have actually finished the paper. I read the first half of the paper, then I skipped most of it, and then I read the conclusions. The issue is that it's an interesting survey paper, and if you really want to actually do something in curriculum learning, you should go through it to see what they've been doing. But at some point, you're just reading what different people are doing. It all kind of blends together and not getting very interesting things out of it. So the presumption was that all the actually interesting parts are inside their own conclusions by me.
Unfortunately, also, they try to cover a lot, which means that they offer no comparison, or I would claim even novelty to what the original papers offer.
I mean, their novelty was trying to group the curriculum learning things somehow. So
yes,
they had
but
this
I would have expected also some kind of, let's say, an information gathering or filtering process from them where they review and go like, okay, not like almost like a meta-analysis that is done in biology and stuff like that, or in, let's say, usually different type of science, other science, where you do like a meta-analysis of very many different studies and you bring the statistical results together to figure out what is better, worse, what is the actual result.
Yeah, I agree that, I mean, this is the best survey. I haven't read that many survey papers in my life, but from what I've read, this isn't like the best one. I mean, it gives a very good overview if you want to have it, but it doesn't make that many comparisons and conclusions, I think, from what I read at least.
Yeah. Let's say it presents many methods, like 50 or something methods. And if I had read the paper fully, I also read about halfway. But having read it halfway, I would not be able to say which one of those methods would be better or worse for me.
Yeah, so the issue is that they're just like describing the methods, but not really like comparing them, I guess.
Yes, basically almost it's like they take the abstract, boil it down to smaller content, and then next paper.
Yeah. So considering how they talked about the banjo, which we had issues with, then
Yes.
but maybe everyone knows something we don't, which is most likely.
Yeah, always possible. But also, let's say there are some very funny examples also to me where it was like a example where it said that they collect information from Google and Flickr, arguing that Flickr data is more noisy, thus more difficult. And when I read that, I was like, if they had gotten an opposite result, they would have said that Google data is more noisy, and would have also been able to publish a paper.
Are they saying that Flickr search engine is worse, basically?
I don't know, but it was so like yes, and but it's just so like.
Yeah. So that is the issue. They're not actually giving. So I don't know if that is the point of the survey, but they're not actually giving their own opinion. Yeah, for example.
Yeah. Maybe basically I expected more like a critical analysis of these different things to show, okay, this direction is good, this direction is bad. No, it was a presentation of all the directions. Basically, they acted as a Google search.
Yeah, but there's still at least that conclusion was interesting, that they think it should be going, at least more thought should be into let's say model complexity change.
Yeah, actually, I take that part was actually interesting, how they generalized the learning tasks, what they their conclusions, their potential direction was also, let's say, we think people should do more of this instead of actually doing that. Could be like a reasonable statement, I guess. But otherwise it wasn't very fun.
Yeah, but so if we, for example, if we get to their conclusion, their main conclusion was that, however, we note that curriculum learning is not always bringing significant performance improvements. We believe this happens because there are other factors that influence performance, and these factors can be negatively impacted by curriculum learning strategies. So their point is basically, if it's not improving, then you're doing something wrong. And then they're providing examples what you can be doing wrong. So one example for that from them is that if the difficult, so this is a very good example. So basically you are doing something wrong. So basically, if the difficulty measure has a preference towards choosing easy examples from a small subset of classes, the diversity of data samples is affected by the preliminary training stages. So basically, you're always taking the same examples out of your distribution from a very narrow subsection.
So yeah, I agree, but also sounds like a cop out. I mean, yeah.
But yeah, basically they're saying that what they would like to see is more research into why in some cases curriculum learning is failing, and what could be done to make it better in that sense. So they're actively interested in finding the failure modes.
Also, to me, when I read their formulation, it made a lot of sense for me to combine the different learning, like different learning, like the curriculum strategies into one, instead of doing them separately. Because to me, it wasn't only, it seemed like a logical thing to do. Yeah, but this kind of is almost like separating models into smaller models that you can conceptually understand. Which kind of was a thing in the past, but then people were like, just add more layers, and that sure at this point has kind of won over making, let's say, custom purpose nets that then bring it together to one big net in the end that does the whole task. If you want it, so end to end versus basically whatever it was called. So once again, to me, it like starts becoming related to a very different discussion or topic that is not called curriculum learning, but it's like also conceptually very similar to. If you take all of these different things, put it into one, then it is basically end-to-end learning versus making separate networks and putting it into one network in the end.
Also, one interesting, I think, conclusion that they also had here is that the only reason we need, basically the only reason we need curriculum learning is because the way we learn is by stochastic gradient descent. And because the gradient descent is stochastic, usually via mini batches or something, then basically we're not always making the optimal decision for the network as a whole. And that's why you need to have optimal training data, kind of.
Wow, I don't agree with that statement at all.
Maybe I was so to read. So I put the quote here. Okay, we should emphasize that curriculum learning is an approach that is typically applied on neural networks. Since changing the order of data samples can influence the performance of such models, this is tightly coupled with the fact that neural networks have non-convex objectives. The mainstream approach to optimize non-convex models is based on some variation of stochastic gradient descent. The fact that the order of data samples influences performance is caused by stochasticity of the training process. This observation exposes the link between SGD and curriculum learning, which might not be obvious at first sight.
What my problem with this is that it's like a chicken and their problem stated differently. So it's once again some kind of a generalization versus not generalization statement, which is very abstract, which is also very hard to check. Is that I would say I can go quickly. I would say stochastic gradient descent is aimed also basically to generalization.
I think SGD is aimed at an optimal way of descent, an optimal way to gradient descent.
Yes, to find the global minimum, basically.
Well, not I mean, no one presumes to find the global minimum, so I won't say that.
Yes, but you do want to get to as close as possible.
You want to find a local minima. I mean, I think the idea has always been to find. You're trying to find the local minima, which is more or less good enough, and usually that happens.
Yeah, I will not get into that. That should be like another paper we go. Why it should be a paper? Why why neural networks achieve global minimum, because I think it's like a totally separate topic which we might want to get into. But I would say that the fact, like their reasoning is because we use like a method to achieve better generalization, we need to do curriculum learning because otherwise, well, it's like because it is random. I don't understand. What
I mean, you still want to be random, but I guess you want to be random, but be smart about it. It's like the same way that it's okay. So let's say human analogy. It's better if you're a child going to first class. It's better that if you have a random sample of classes that are meant for first grade people, then you have a random sample of classes meant for all the 12 grades you're in. You would be in 9 grades, whatever. I guess. But then while you think about it, they also actually pointed out the negative because of this. Since curriculum learning usually implies restricting the set of samples to a subset of easy samples in the preliminary training stages, it might constrain SGD to converge to a local minimum from which it is hard to escape, as increasingly difficult samples are gradually added. So actually,
exactly that was my problem. Thanks for formulating it for me, Peter.
So basically, they're saying, so that it's harder to control the optimization, so it will require some kind of babysitting, and they think that this is a thing. So most likely, this is one of the issues the curriculum learning is having, and so they want to see more research into this area.
But if they are, let's say, dealing with the consequences of SGD, then why not manipulate the parameters of SGD, not actual curriculum learning?
But maybe this is kind of, you are kind of.
Well, yeah. I mean, that's my point. You are. So once again, this is what this comes back to. Based on these examples, it often feels like the magic trick is not the curriculum learning, but the magic trick is it is influencing something else in the system.
I mean,
influence the results basically.
I would think about it as we got like some. Frankly, someone really thought someone figured out that SGD is a very good thing to use, and it was yeah, that's really good. But of course, everything has its drawbacks, right? Even if you don't know about it, and then someone found out that if we do this curriculum learning, then that is actually good. And then when you think about it, then this just actually is trying to fix some of the deficiencies with SGD. I think, as far as I've heard podcasts, like there are like people believe that we won't have gradient descent forever, that someone thinks about something better. But this is basically just trying to trying to work within the constraints that we have.
I think to say 10 years ago, it was very popular to say boo gradient descent is like a trivial thing, just like a stepping stone.
Yeah.
And then it's like you get the crazy good results, and then everyone's like, wait, we actually, so if we really think about the math, gradient descent is pretty nice. We get this real manifold and etc. And like, maybe that is actually what we do want, then we need something else somewhere else, not actually in this step that we're talking about. And I also maybe was also like a few years ago, knowing even less than I do know about today, just having played around with neurons a bit, be like, why is everybody doing gradients, and go do some cool genetic algorithm based weight optimization or whatever the heck you want. But yeah, I think nowadays gradient descent is still too popular to be like at some point you might need to consider maybe these actually fundamentally good for some very important reason.
Exactly, funny that you say genetic search, because perhaps, or again quoting from the article, Perhaps an even more promising direction is to couple curriculum learning with learning strategies with alternative optimization algorithms, example evolutionary research. We can go as far as saying that curriculum learning could even close the gap between the widely used SGD and other optimization methods.
I'll believe it when I see it.
Of course, but I think it seems like a very active area of research.
Yeah, I mean, it is something that everyone wants, though. Very importantly, I think like the intuitions and stuff like that here is still very important, and it's like the promised land, which I shared this Darpa into you.
Yeah,
I
will share it in a second.
Yeah.
So do I go straight to the end, or no? Basically, this one.
You can do what you want. Your turn.
My turn. It's you chose this.
I know, but I can go myself, or if you want to.
I will start and you will finish. So basically, I don't know what this presentation was about, but at least apparently, I mean, Hendrik showed it to me, and apparently it's from DARPA on artificial intelligence, I guess generally. I presume this is for quite the general audience. So they talk about like the three waves of AI. Well, currently 3 waves. Let's see how many waves there are. So in the beginning, we started with handcrafted knowledge. So basically, we had a lot of, I mean, most likely still have at some points, you have a lot of like feature engineering, which is very important. So basically, people study what features are the most important. We run the algorithm, see what features are actually useful. Then you do some magic with some of the features, and so on. Then you kind of handcraft and you pick the knowledge that the machine learning algorithm will use. And then they say that this is enables reasoning over narrowly defined problems, but it has no learning capability and poor handling of uncertainty. And then after that, you go to the second way, which is statistical learning, which basically means that you just throw all the data at the network. The network is smart enough now, and it will figure it out itself what is useful and what is not. And you just try to make the network as good as it can be. Usually this is, I don't know, so the machine learning is of course still used in a lot of places where it's useful, but I guess this goes in more basically it means using neural networks, I guess more. So this is without neural networks. Might be a wrong statement, but that's what I think about it. So basically engineers create statistical models for specific problem domains and train them on big data. So big data is, I guess, a buzzword everywhere now.
Yeah, I mean, I will comment this that I think this is like a general thing that I would like to share, like to business people who are like trying to sell machine learning. When you're doing something with machine learning, you can give them this. It might ground them a bit, but that it's a level of knowledge. It's at the level where they will understand it. But there is some interesting points in the end also regarding where we want to get to, I think.
Yeah, and so what DARPA says about the second wave is that you have nuanced classification and prediction capabilities, but no contextual capability and minimal reasoning ability. So still, in the grand scheme, a lot of issues. And then you get to this manifold hypothesis. So basically, you have the idea that if you get down to it, all the data lies on some kind of with low-dimensional manifold. And if you can just figure out that manifold, then everything will be great. And then the neural network kind of tries to figure out what the manifold actually looks like. And of course, it has some kind of issues. And then you so of course, the issues that you have is that you can have individually very stupid things, like a young boy is holding a baseball bat, when a baby is holding a toothbrush. Or I guess the most widespread issue is that if you have knowledge, sufficient knowledge about the neural network, if you add like distortion, which is just noise, then you can make a panda into a gibbon. Or I guess when I think this was by Microsoft.
Yeah, I think so.
But anyway, Hitler did nothing wrong. So basically, they created a chatbot, and then trolls messed with it a lot, and then they had to shut down the chatbot for apparent reasons. So basically, you have to really see what your training data is all about.
That was a very fun 2 days.
and they can talk about the contextual adaptation, the third wave.
Yeah. So basically
and how it relates to today.
Yeah. So basically you can scroll a bit maybe to the next slide straight away. So the main problem that we have today is you could say what people have classified as explainable AI, or understanding what the model actually does on the inside. And why we would want to know that, and why we would also first let's go with why we would want to know that is we want the models to be predictable. We don't want them to have unpredictable results, and if they do have unpredictable results, then we want to handle them in some way in many real case scenarios. Having said that, with neural nets, they're statistical models, they will never be perfect. But internally, we also want the neural networks to be structured in a way that they have explainable interfaces. And this is because we want the level of knowledge that they infer to be something that both neural nets can reason about, and that humans can also reason about. And I think there are good examples when we go to the next slide. So basically, that the intermediary neural network. So this is basically instead of having a traditional end-to-end, let's put everything in, you would have some kind of basically neural network structures where some neural network would create something similar to, I would claim it would consist of something similar as these OpenAI large OpenAI GPT-3 models, and generate statements of reason, and then from these statements of reason a classified output is made, and then you can analyze both the statements of the statements of reason and the output, and therefore optimize for also like this reason and explainability, not only the classification accuracy. And yeah, so that's the holy grail of AI that I would say everyone from I would say that's the holy grail of AI, which people actually want. And when they imagine AI in their head from as a non-technical person, that is what they imagine it to be, and what is like the direction also funded by, for example, Darpa in this case, which is interesting.
Indeed. And how is it related to curriculum learning?
Curriculum learning. To me, it seemed like the curriculum learning also wants to separate. So it is almost kind of like separating things into learning some. Actually, I would say this is like the top-down, bottom-up distinction once again, which is like this is learning statements, statements you can reason about, and building up the classification from that. And I would say this is also almost like curriculum learning, but the way of how you state the problem is different. So what do you optimize for?
So you don't have a context. It's like the first step, I guess. One of the first steps, I guess, to the third wave. You have like a contextualizing the data sets.
Yes, and like yeah, in some way it is like making. I don't know. To me, it was in my mind a bit connected when we thought about this survey paper about this, making a model and then extending that model with different curriculums. And I don't know, to me, in my head, it connected a lot. I'm interested on what you think. Did it connect similarly for you?
I think it does. I think I just you have thought more about it. I just saw this today morning.
I
So
also saw
I
this
don't
yesterday. It's a Hacker News post, and it's like, ooh,
exactly what I needed.
yes, exactly.
I think it is interesting. I mean I would say I guess this is one thing. This is definitely one definition on what are the waves and what is the future of AI. But it seems like reasonable and logical. And it seems to I think there is like a difference between there's definitely difference between how I usually I'm still very novice in all of these subjects, but what I usually think about also GPT is like it's big data. You throw more data onto it, you see what happens. You increase the capacity of the model, which is also kind of what the neurocomputers are doing. You increase the capacity. Just now you have another extra dimension where you can increase the capacity, which is the memory. Which is also interesting. I would like to have GPT have also memory and see what it does then. The whole different thing. But what do I want to say? But yeah, you're starting to. I guess it comes back around. You start with very strictly defined. Very strictly defined learning algorithms, very strictly defined data, and then you're like, oh no, now we have very large GPUs and we can just throw the data into it and see what happens. And then you're like, oh no, we're getting some really freaky edge cases. What the fuck do we do? And then you start thinking about it. Okay, how do we now logically or very smartly reintroduce the good parts of the part one back into part two, and we can get more information out of it.
Yeah.
I don't know if this is. I think most likely not all people agree with this third wave. Some people I think are in the camp that just throw more data out of it and have a larger model, and all other issues are pointless.
I think the throw more data into it, as I described the GPT model. I think it's a node in the system, a very critical node.
Yeah.
But a node in the system that exists in this formulation of feature thing, and the way of how we separate it and how we categorize them might either come from this contextual learning, curriculum learning, or somewhere else. But still, I think it's like building up from that, and basically combining different networks like that. But that's just, once again, who knows what the future brings. It's like we'll see.
Yes. Okay, I think this is a good place to wrap it up. So what we talked about today was basically curriculum learning, and the main idea behind it is starting with an easy solution. Either is it easy because your model is simple? Is it easy because your examples that you're feeding into your model are simple, or whatever? How you define simple? You start with easier basically problem, and then you start making it more difficult either on the model side, so you can give more expressiveness to the model, so you can handle those edge cases. So basically, in the beginning, you start to head towards some kind of local minima. If that being good, that local minima being good or bad, it depends on how you set up all the issues, and that's still an area of research. But basically, you're starting with a smooth. I'm throwing different words into it, but basically, you're at least like give, let's say, the model a general direction where it should be heading, and then you start giving it more difficult examples. And of course, as you see that, and at least from our, I guess, idea that even if it's like a very important paper in the scientific field, basically introducing a new idea to neural networks specifically, or not, yeah, introducing a new idea, that doesn't specifically mean that the paper itself is the greatest paper. But at least idea was worth it. So yeah, I guess that is one of my main takeaways, is that even if the paper is bad, doesn't mean the idea itself is bad. And also, I don't know, what is your main takeaway from today?
My main takeaway is actually, in some context, I kind of expected more. from the maybe especially because it was 2009 and then we have the survey paper basically 12 years later, and I would say I would have expected the curriculum learning approach to progress more, but as we mentioned also last time, it was used in some cases for in DeepMind for some specific applications, so it might also be kind of in somebody's toolbox and they are using it, and we haven't really, let's say, found the source of what is the, let's say, quote unquote good curriculum learning that you should use every day.
Yeah. Also, if maybe we didn't read the correct papers, and if you said if you're watching this and you think, oh, you stupid boys, you should have read this paper, this will explain so much more than these bad papers, then please share the paper and we can maybe read that paper next time, or not next time, but at some point. But yeah, we haven't really thought about the topic for next time yet. I guess we will talk about it later. And yeah, I guess that's all. Thank you for listening. Like and subscribe and ring the notification bell. The first person to subscribe gets a shout out.
Exactly.
The first person to watch this video that isn't my mom gets a shout out.
Anyways, yeah, thanks for listening, everyone.
Yeah, see you next time.